Thank you.
Don't let your soul leave.
Okay, so let's talk about the lab from yesterday. And this is just kind of the nature of science. You have to sometimes just extrapolate data. So you don't have every velocity at every point in time. Okay, you don't. But you kind of can think your way through it. So let me ask you this. On the way in, okay, on the way in, when did it have its biggest positive velocity?
After push.
Right after it left your hand, right? Because you have two different types of mafia that are in play. You have the frictional mafia and you have the spring mafia, okay? And the spring mafia involves energy, okay? So here's the story. So as the cart was rolling, it was slowing down a little bit, okay? So whenever you look at motion, again, there's only two options. You either have constant velocity or you have accelerated motion. That's it, only two games in town. And if you have accelerated motion, it's either slowing down or it's speeding up. And if you take it to the next thing, which is going to be this unit on forces, oh, that's F equals ma. So if you have an acceleration, that means you have to have a force, okay? That's it, those are the rules. You don't have a force, you don't have an acceleration, your velocity doesn't change. Simple as that. So when you gave that car a push, and it was rolling along, right? And this is what I want you to realize on the back side, that last question in the back. So you have some V1, okay? You gave it some positive velocity. Now, as it's rolling, which mafia is affecting it? The frictional mafia or the spring mafia? Alex?
Friction.
Friction. Now, the frictional mafia is relatively, of the two, the frictional mafia is the weaker of the two, okay? Because it's only impacting the wheels. So what I want on this back side, okay, on number 13, you've got that V1. Now, you're going to draw V2. V2 is either going to be bigger or shorter than V1. Deacon, what's it going to be?
It's going to be small,
Is it going to be a lot smaller?
only a little bit,
Why?
because the friction mafia is only affecting the cart a little bit.
Yeah, so you're going to draw V2 just a little bit shorter than V1, okay? Connor S., is the cart accelerating because of the friction mafia?
Yes.
Is that making it speed up or slow down?
Slow down.
So which direction is my acceleration vector going to point? In the same direction as my velocity vectors or the opposite direction?
Opposite.
Is it going to be a relatively big acceleration or a relatively small acceleration? Because the frictional mafia, it doesn't do much, okay? So I'm going to draw a relatively small negative acceleration vector, okay? That's what I want up here in this top left corner on number 13. You're going to draw a V2, a little bit shorter, and then you're going to draw a short acceleration vector in the opposite direction. Now, bam! Shouldn't have said that loud. Oh, my voice is a train wreck today. When it hits the wall, now which mafia is involved?
Spring mafia.
Spring Mafia goes, you're a good boy, right? Spring Mafia sends the big heavy hitters into this game. So again, you're going to draw another V1. Now, since the Spring Mafia is going to be involved, what's going to happen to V2? Is it going to be a lot smaller or just a little bit smaller?
A lot smaller.
A lot smaller. So there's going to be V2 because it's going to slow down rapidly because the Spring Mafia has a lot of muscle behind it. Okay. So is the acceleration going to be a relatively big value or a relatively small value? Sydney,
Relatively big.
because it's the Spring Mafia, right? So which direction is it going to go? Same direction or opposite direction, Sydney?
Opposite direction.
So now you're going to draw a big negative acceleration. Okay? Does that make sense? Now, this is gonna correspond with your velocity time graph. Now, I looked at Alex's data. If you're in Alex's group, the most critical thing that you have to worry about is the lapse time at the end of that second interval, because that's when your velocity goes to 0. So Alex's elapsed time was 2.34 seconds, whatever yours is. So at 2.34 seconds, so there's 1 second, 2 seconds, 3 seconds, 4. So at 2.34 seconds is when that velocity time graph has to hit 0, okay? You cannot play connect the dots. Your velocity time graph cannot look something like this, okay? Because if your velocity, if you spread that out and you connect the dots, unfortunately for 12 years of your educational careers, you've been taught to connect the dots, okay? That's what you've been told to do. Well, here's the problem. If this line stretches out like this, it looks like from the time that it hit till the time that the spring expanded, took like 3 seconds. Did the spring take that long to happen?
No.
No, it was very short. Basically, it took about that much time. Enough time to snap your fingers twice. Okay, boom, boom. That's how long it took. But if you draw it like this, it looks like it took a long time. So here's the most important thing. Your position time graph and your velocity time graph have to show the same thing happening at the same time. It's going to look differently, but they have to show the same thing. So your position time graph is going to look something like this. If I'm Alex, that relative maximum is going to occur at 2.34 seconds. Then what I would do is I would draw your velocity time graph directly underneath that and use the exact same time scale. And whatever time that hits a relative maximum is when that velocity time graph has to go through 0, okay? Because they both show the same thing at the same time, okay? Because this is when this instantaneous velocity goes to 0. That's when your velocity time graph goes through 0, okay? Cool with that? Got that? Now, the problem is you have to think through this. At time 0, you're going to have your biggest positive velocity. You don't know what that is. When you calculated the velocity over that first 1.5 meters, that was the velocity over that interval. It was probably going a little bit faster at the beginning. It was probably going a little bit slower towards the end. So when you calculated that velocity, that was kind of like a midpoint along the way, okay? Then you had a second positive velocity, which was probably a little bit slower. So your velocity time graph at the beginning is going to be coming down like this, okay? This initial point here should be higher than what that first calculated velocity is, because it was probably going a little bit faster at the beginning, okay? Now, if I'm Alex, and his time was 2.34, I'm going to shift back 1/10 of a second and go to 2.33. That's when that plunger is going to hit. Now, F equals ma. It's a simple idea, but it's very profound. The only way you can change the acceleration is by changing the force. When the plunger hit the wall, did the force change? Yes. Therefore, that changed the amount of acceleration, which changed the slope of the graph. So, bam, the plunger hits the wall, bounces back, okay? So, I'm going to take this line down like this. So, this is going to be 2.33, that's going to be 2.34, that's going to be 2.43. Now, you know a couple of negative velocities over here, here, and here. But again, think this through. Connor A, on the return trip, when does it have its biggest negative velocity?
Right after the spring is complete.
Yeah, right after it leaves that wall. Because after it leaves the wall, which mafia is gonna make it slow down?
Friction mark.
Frictional mafia, okay? So you have frictional mafia, spring mafia, friction mafia, okay? That's what you got going. So the problem is you don't know what this point is. So what you've got to do, again, this is called extrapolating data. So you're just gonna have to guess, because you need to know these 2 points. So take a line like this, bring it down, have it match this line coming down here like this, okay? So when you get done, this is what it should look like. I'm gonna tell you straight up, here's the most critical thing I'm gonna look at. I'm gonna look at Thatcher's graph. I'm gonna look at the elapsed time at the end of that second interval. And that better be where that velocity time graph crosses 0, okay? Now, one of the things that you wanna do is you wanna find this area. So what I would recommend is treat this like a rectangle. You can do triangles and rectangles, but it's a god-awful amount of work, okay? So what I would do is I would just come up here and draw a line that kind of catches the midpoint of that slope, okay? And call that, whatever that velocity is, okay, kind of at that midpoint. And then I take your time, like with Alex, I might use like around 2.34 seconds, something like that as my base. And then use the height as whatever that is. Then it's just a simple rectangle. Then I'd do the same thing down here. I'd come down here and I'd do something like this. Come down here and kind of split this line across like this, and then have that negative velocity. But you have to be careful. With this one, you have to use the time from here to here. Don't use the entire time. Just use the time from this point to this point. Again, everybody's numbers are gonna be different. The only thing I can grade is your work. Make sure that you have numbers, make sure that you have units, okay? Now, down here at the bottom of the front page, I have listed 3 bold arrows of everything that you need to do on that velocity time graph, okay? Do them. If you're not sure if you've done them, ask the person beside you, hey, can you figure out when it hits? Can you figure out when it expands, okay? Oh, the papers that I've graded so far, if you were my employees, the vast majority of the kids' papers I've graded so far, I would fire all of you. No, it's a true story. Like, they didn't follow instructions. I can't see when it's positive, negative. There's random things written down, literally. Probably out of the papers I've graded so far, I would fire 75% of the kids if they were my employees. Okay, true story. Like, you're fired, get out. But I'm smart, I don't care. Mom says I'm special, don't care, you're fired. You can't follow instructions. So, no, first block, they are dead meat tomorrow. My first block is, they are toast.
Can you record it?
Literally 6 of the 7 are fired.
Who's not fired?
Can't say.
Can't say.
And even then, that person's on probation.
Sorry.
No, the 7th is on probation, the other 6 are, pack your stuff and get out.
Are Phil and Danny tired?
Well, it's the graph. They didn't follow the instructions on the graph. Okay. When you're answering questions 2 through 6, be very specific about how you answer that. Just don't say, well, it happens at the wall. Okay, there's a whole bunch of things that happen when that plunger is in contact with the wall. The plunger is being compressed. The plunger is expanding. The plunger is fully compressed. It hits the wall, it leaves the wall. There's a whole bunch of things that happen when it's at the wall. So you just can't say, it happens at the wall. It's too vague, okay? It's way too vague. All right. Anything else you want me to go over? Going once, twice. pow, you're done. So staple the graph to the back. If you're not sure if your graph is right, ask someone else in the class. If they flip out, I know I'm going to flip out. So stop.